David, you've had a remarkable career, more than 50 years in quantum theory, relativity, much pioneering work. Reflect back on your career, on your thoughts, the development of the field. What insights can you give?
Well, the starting point for me was this understanding that quantum theory forces you to give up the old logic and replace it by a new one. This was spelled out pretty explicitly by Heisenberg and Bohr, and a lot of people have pursued this besides me. The simplest way I have of understanding the new logic is that you really turn your attention away from objects toward processes. They become more fundamental than the objects. We used to think of processes as things one object does to another. And no, objects are defined by the processes that are carried out on them.
So process is more fundamental than object.
That's the way I've had to think about it, simply because quantum theory is almost entirely a language of processes. It's full of things called operators, and oddly enough, they represent operations. And the whole language is just operators, so it's all just operations. There are two nouns floating around, but they're fixed, so they need never be mentioned. Namely, there's the observer who does the operations, and there's a system he's studying on which the operations are done. But they're fixed things, so they don't even occur in the language. All we ever talk about are the operations. So this replaces the old kind of object ontology by what might be called a process ontology, but that's almost a contradiction in terms, because ontology is about being, and process is about doing. I haven't been able to find a good word to replace ontology, except possibly dynamics.
Now, does this impose real fundamental change in a reality, or it's just a different way of expressing the same thing?
Well, I guess it's a fundamental change in that now real is a four-letter word. I mean, real means thing-like, and there are no things for me. So real is very unreal.
Okay, so real.
By the way, when I presented some of these views at a conference at Columbia, one of the participants, Dalai Lama, took to calling me Mr. Actuality, because I'm happy to say things are actual when I'm unhappy to say they're real.
Okay, define
because of the root, actual, act. Actual is what's going on, not what is.
And so therefore, the word actual has more of a process field.
Exactly.
Whereas real has a more of a static permanence.
Right. I find that one of the big traps is objectification. And calling things real tends to make you think they're real. And calling them actual I find safer. I stole the word from Alfred North Whitehead, the English philosopher.
Now, I want to get my hands on the difference between actual and real. Actual, you're saying, has a process part to it, but when you're saying that things are not real, I mean, what does that really
It really
mean?
means you're shifting your attention from the objects to the actions.
But does that really mean that the objects are really not real, or just as you should now pay more attention to the process as opposed to the object?
If you look into what people mean when they say that things are real, it turns out, whether they know it or not, they're saying they obey ordinary logic. Either A or not A, not A and not A.
At the same time.
And A and B or C is the same as A and B or A and C. They apply ordinary logic to real things. Saying they're real means you don't have to worry about what happens to them when you know about them. You just know them as they are. And that's all bad news for quantum mechanics. You don't know things as they are. In relativity, we learned you know things as they were, because it takes time for the light to reach you. And in quantum theory, even that goes because the light changed them on the way. So
you can get into a notion where everything sort of dissolves if you think too hard about it.
unless you focus on the actions. And even there, you have to give up trying to say too much about yourself. Just say what you know. I do this, I find that. I hold polarizers this way, hold another one this way. Half the time the photon goes through. And you can get away with ordinary language as long as you're talking about ordinary actions.
And then from this, you're actually predicting real results that is very quantitative, very predictable, and very certain that are real results.
I would say that quantum theory is the most practical physics there is. And I like to say that in the root sense. It has to do exclusively with practice. It's practical in the sense of being pragmatic. For me, it fits into the philosophy of Charles Sanders Peirce, the American pragmatist. Mm-hmm. But that's a matter of taste.
And what are some of the areas that you've dealt with in your career from this perspective?
The first thing I wanted to do was make sure you couldn't easily make models of elementary particles out of ordinary, continuous, old-fashioned space-time. Mm-hmm. And could I borrow your belt? I'll show you a model of an elementary particle.
All right. My belt normally has much more pedestrian uses, but I'd be happy to.
Okay. By the way, in physics, there are 3 important belt tricks. This is just one of them. Okay. The one who introduced these tricks is Paul Adrien Maurice Dirac, one of my heroes. And this model for an elementary particle is called a skyrmion. It was studied by the physicist Skyrm. If you have a belt like this and you put a twist in it, if you hold the ends fixed, the twist can run back and forth, but the number of twists is frozen.
Yes.
It's either there or it's not there, or you can have 2. 2 can collide, and 1 can come out on either side. So they behave very much like elementary particles, except they're not at any one point. Mm. They're distributed. Okay, so those are the skyrmions.
Yes, so the twist can go all the way up and down.
Right. And there's a whole mathematical theory of the collisions of these twists that has been worked out. Turns out that this is also a pretty good model of what can happen in space-time. Mm. This I do with my fingers. In space-time, you have these little arrows telling light which way to go. They form what are called light cones. And if you think of this as a time axis and this as a space axis, then here is a little skeleton of a light cone showing might be a spark, and here is a ray going off in one direction. Here's a ray going off in the other. It's actually an expanding sphere of light, a ball of light. Mm-hmm. But this represents it. And then in a gravitational field, these light cones twist and sway like lilies in the wind. Mm. That's gravity, the bending of space-time. And this is a gravitational skyrmion. There's a full 2 pi rotation, a full circular rotation of the light cone from one side of the world to the other side. Mm. And if that happens coming in from all directions, that structure is so entangled in space-time that it cannot be ironed out. You have to cut to get rid of it. You can move it around, it behaves like a particle, but you can't get rid of it. It's an absolutely conserved structure.
So what's the implications of that?
That, unfortunately for my program, it is possible to make particle-like structures out of space-time. I call them kinks, but I think they can be called gravitational skyrmions. Mm. They come right after skyrmion's thought. Looking at them, I noticed that each of these things surrounds itself by a little shell where all the light is going in and none is coming out. Mm. So this was my first encounter. I called it a unidirectional membrane, a real catchy name. And it was renamed black hole. Oh. Right? And people had been studying them in general relativity for a decade or more before I came along. I didn't know about it. And I was really disappointed that it existed, but I wrote it up. And it turned out to be useful for understanding the structure of the gravitational field of a point particle. It triggered a lot of the early work on the black hole. But for me, it was something I had to leave behind because I wasn't interested in the continuum of space-time. I was sort of disappointed that it had this richness in it. I wanted to explain elementary particles using quantum space-time. That was the direction I actually took then.
So, reflecting back now on your entire career, more than 50 years.
Oh, I can't reflect back on my entire career because most of it is in the future.
Okay.